Bismillahirrahmanirrahim. Assalamu alaikum. In last class, we have talked about the following things. So we have defined that if we have a poset and a subset of S, then we can define the upper bound of this subset of S for each for some C in S, as that A is less than or equal to C and B is less than or equal to C. Then C will be an upper bound of this subset. And then if C is there in the S, then lower bound of this subset is going to be, C is going to be lower bound of this subset if C is less than or equal to A and C is less than or equal to B. For an upper bound, these two elements should be less than or equal to C, and then for a lower bound, C should be less than or equal to A and B. And then we can also say that an element D inside the S is least upper bound, which we call LUB, of this subset if A, number one condition is that this D is upper bound, and then for upper bound for which we have these two conditions, and then for C in S, which is an upper bound of this subset, we have D is less than or equal to C, then it will be a least upper bound. Now, similarly, if that element D is the greatest lower bound, GLB, of the subset, if first it should be lower bound, for that we have these two conditions, and for C, which is a lower bound of this set, C should be less than or equal to D, and then that's how D will be a greatest lower bound. We denote the lower bound of the set for a poset by this symbol, and greatest least upper bound by this symbol, and greatest lower bound by this symbol. And Zone's lemma, which is very important, it says that if every chain in a poset has an upper bound in the set S, then S contains a maximal element. And we have defined the maximal element in the previous lecture. Okay. Now, let's start the part 3 of this lecture. We have a definition says that 1.4.17 says that a poset L with this partial order is called a lattice if it has a lower bound, it has least upper bound, and a greatest lower bound exists. In L for all A comma B inside L. So a poset is called a lattice if the poset has a greatest lower bound and a least upper bound. Example, the best way to learn things is giving examples, by examples, every time. So let L is an closed set 0, 1, which can be written as that it contains all the real numbers such that they are between 0 and 1 and 1, 0 and 1 included. Then this is a poset. It's a poset where this denotes the usual less than or equal to relation. Then let A comma B are from L. Now the maximum of the set A comma B, which is inside L, and minimum of the set L comma A comma B, which is also inside L. And it is easy to see that maximum of A comma B is least upper bound of A comma B, and minimum of A comma B is greatest lower bound of this set. For example, max of 0.2 comma 0.3 is 0.3, which is 0.2, 0.3. Least upper bound. And similarly, minimum of 0.2 comma 0.3 is 0.2, which is 0.2 greatest lower bound 0.3. Hence, this is a lattice. The example we have been using for a very long time, good time, which is we have a set S. We have a poset with the sign where this relation is a inclusion. set inclusion, or you can say set inclusion relation for two sets A and B inside the power set of S. We have A, E, A least upper bound is B least greatest lower bound. B greatest lower bound. Sorry. A least upper bound is going to be A union B. We have defined that before. And then A greatest lower bound is going to be A intersection B. Hence, P of S with this relation is a lattice. So simple as that. If a poset have least upper bound and a greatest lower bound, then it is a lattice. Theorem, where we define some properties of the lattice. So let's define a theorem which is 1.4.20. Let L be a lattice or a poset, be a lattice, and A, B, comma C are in L. Then number one, or we can also write for the clarity that there is L1 property, which is A least upper bound, B is B least upper bound A greatest lower bound B is B greatest lower bound of A, and this shows it is a commutative law. L2 A least upper bound B least upper bound C is A least upper bound B upper bound C. Similarly, A greatest lower bound B greatest lower bound C is A greatest lower bound B greatest lower bound C, and this is associative property or laws. Now L3 is A greatest least upper bound A is A, and A greatest lower bound or greatest lower bound A is A, and this is idempotent law. And there is L4, which says that A greatest lower bound A least upper bound B is also A least upper bound A greatest lower bound B is also A, and this is absorptive absorption law. These are straightforward. There is no need to actually prove them explicitly. But if someone wants to prove them and they don't understand, just comment it in the video, and then I'll try to show you the proof in the next lecture. Then we have another theorem, which is 1421, which says that late we have a poset and there are elements a comma b from the set S, then following conditions are equivalent. Following conditions are equivalent. This is the proper shortcut to write it. Following conditions are equivalent. Number one condition is less than b or equal to b. That is, whatever the relation we have with the poset for this sign, these two elements inside the S will follow that. Number two, a least upper bound b is b. If this is the case. Number three, a greatest lower bound of b is a. Perfect. Then we can define another type of the lattice. By definition, so a lattice L with this relation is called a modular lattice if for all A, B, C inside L, where A is less than or equal to C, implies this condition for between two elements implies that A least upper bound, B greatest lower bound, C is A or B and C. So usually we say and in be written like this, and sorry, and can be written like this, and or can be written like this. So if you want to read them, not LUB and GLB, you can read like this also. Okay. So in previous two examples, so you can say that the example star, which we have in example hash, the examples star and hash have modular lattice. Perfect. Let's define one more example. It says that consider Consider the lattice given by the following diagram. So we have a diagram. We have one here. We have one here, B here, C here, A here, and 0 here. And let's connect those. Now here, A is less than or equal to C, but A and B or C is A and 0, which is A but not C. And or C, where C is A or B and C. Hence, this is not a modular. This is not modular. Because the conditions we are trying to satisfy are not satisfying. So that's why. Because we have a condition that A and B and C, A or B and C should be equals to what? Should be equals to A or B and C. So that's how they are distributive. Now we will define the distributive lattice. We have defined the modular one. Now we will define a distributive lattice. Definition. So a lattice L is called distributive if it satisfies condition B1, which says that A and B or C is A and B or A and C for all A, B, C inside L. The lattice is an example star and hash are distributive. Are distributive. Theorem. A lattice L is distributive if and only if we have a condition D2 that A or B, A or B and C is A or B and A or C. And that's the other condition for the distributivity for all A, B, C inside L. Now we can prove this. Suppose this lattice is distributive. We take A, B, C from L, then remember lattice is distributive, it has this property, but now we have this property also. So we will take what we will take the other side, this side, we take this side and write it that A or B and A or C can also be written as A or B and A or A or B and C. And this is by the condition D1. Why? Because D1 says, the condition D1 says that if you apply this from this side, if you do this from this side, you will get this part A or B only. And then if you do this with other side, you will get A or C only, because when you will do A and A, it will be A, because A and A is idempotent, so it will be equals to A. So that's how. And now if we move further, we can also write A and A or B, or A or B and C. And this is by L1, the property, first property of the lattice. And now we can write it A and A or B and C. This is by L4, which is absorption. And then again, we can also write A or C and A or B. And this is by L1 again, commutativity. Then we can write A and C and A, C and A, or C and B. This is a distribution property clearly by D1. And then we have A or C and A or C and B. And this is associativity, L2. Then we can also write by L1 commutativity, A or C and A or B and C. Here, by commutativity, and then we can combine them by the absorption, and we will end up with A or B and C. So hence, A or B and C is A or B and A or C. Similarly, we can go from D2. So D2 implies D1. Another theorem which says that 1.4.26 says that every distributive lattice is a modular lattice. You can also write the proof, which is simple. So we have a lattice distributive, and we take elements from it such that A is less than equal to C. Then A or B and C is nothing but A or B and A or C, which is similar A or B and C, because A is already less than or equal to C. So that will be, so the answer for this one is C only. So because this has this property, and then this one is only C. So hence modular lattice. Perfect. But the converse is may not true. So every distributive lattice is a modular lattice, but it's not true for every modular lattice that would be a distributive lattice. So example, consider the diagram, the lattice diagram. So we have a poset 1, A, B, C, and 0. Let's connect them. Perfect. Now this is a modular lattice, but not a distributive lattice. Why? Since A or B and C is A or 0, which is not 1, where 1 is A or B and A or C. The last theorem says in a distributive lattice, A and B is A and C, and A or B is A or C. Imply that B is C. For all A, B, C, and L. We can prove this. Now, B can be written as B and A or B, which is also A and A or C. Right? And which is also by the distributivity B and A are B and C. And which is also equals to by the commutativity A and C, or B and C, which is equals to C and A or C and B, which is equals to C and A or B. So this is just C, and then now this can be written as like this. Yes. So by the distributivity, backward distributivity. So if that's the case, this is the case, then we can write this can be written as C and A or C. Why? Because A or B is A or C. And this is nothing but C only. Perfect. See you in the next session. Take care.